All right.
So I got close to the same answer. I was like,
Okay, so how are we going to do this? They want us to find the shaded region in the graph. How are you going to do that?
makes sense. Gotta use the function.
Got to use the function, sure. Okay. So this is, it looks like we're looking for an area that's going to extend from 0 up to pi thirds, right? Okay. But the area under the red curve is not what we're looking for, right? The area under the red curve, you know, this area right here is not, whoops, that's not red. This area right here is not what we're looking for. Right? The area under the blue curve, which isn't a very exciting curve, is also not what we're looking for. Right, here's the area under the blue curve. How are we going to find the gray curve, the gray area? How do you use both of them there? No, you're on the right track. How could we use both of those areas to find the gray area? Subtract. Yeah, there you go. Subtract which one from which one? Yeah. Yeah, there you go. Or blue, subtract the red from the blue. So blue minus red, right?
Yeah.
That's it. Everybody see that? That's all it is. This is just an example. You guys have done stuff like this many times in the past. You ever remember seeing problems like this back in geometry, where they'd say something like, we've got a square and there's a circle inside the square. If the square has side length 10, you got to find that area. How would you do it?
Find area of the circle.
Okay, the area of the circle, what's the radius of the circle going to be?
5.
5. Okay, so you find the area of a circle with radius 5 and subtract that from
100.
100. Yeah, good. So that's what we call area by subtraction, right? So this is just a calculus version of that problem, isn't it? Right? In other words, if I want to find the area between curves, all I have to do is just subtract the integrals. That's really all I'm doing, is just subtracting the two areas, right? The small one from the big one. Does that make sense? Okay. So this just becomes then, well, let's do, here we can even color code this, can't we? So this becomes the integral of, what's the top function? What is that? What's the blue line? 4, yeah. I can put the 4 out front even, right? Because that's a constant. So I just get the integral of 4 dx from 0 to what? Pi thirds, yeah. Right? Minus, and I can put the 4 in there, inside the integrand if I want to. Whichever you're more comfortable with, doesn't matter. But we can pull it out front, can't we? Because we know we can do this. If I can take that constant out front, right? Right? That make sense?
Yeah.
Okay. Okay, minus the red area, which is the integral of what?
3 cosine x plus.
Okay, how would if I wanted to write that integral as one integral, what do I need to do there to that function? Well, I can't pull that constant out. You see? What do you mean by that? Well, I can't take it out separately. I could break it up into 2 separate integrals if I wanted to. But what I was getting at here is that I need to put, if I'm going to treat it as 1, I need to do that, don't I? Okay, do you see why? I just want to draw your attention to that, just so you understand You see that really is what we're doing here? We've got this is the function under which we're adding up area. But if I'm gonna multiply by dx, if I didn't put the parentheses there, it would probably be implied what we were doing, but it would look like we were just doing the dx times the 1, right? Now I could, if I wanted to, I could separate that into two separate smaller integrals. That's fine to do. If I did that, and I don't want to, go into, we don't need to do any of this stuff, but if we did, I just want to point out a couple formalities that come with this integral calculus. If I broke it into two parts, then the 1 wouldn't even right, would I? Then I could pull the 3 out front, couldn't I?
Yeah.
Okay. How come I can pull it out here, but I can't pull it out here? Okay, good, because it's a factor here, but it's not a factor of this function, is it? I'd have to be able to factor it out of both terms to divide it out front, right? Okay, make sense? Okay. And then my limits of integration would just be the same, wouldn't they? So that's really it, okay? What's the area, what's the blue area gonna be? The integral of dx is x. Yeah, derivative of what is dx, yeah. So we end up with 4 times x from 0 to pi thirds. This, stop me if you have any questions about any of this, even tiny questions. So far, so good? Right? Minus, what's this antiderivative going to be? Okay, 3 sine x. Yeah. Okay, plus. Okay. Now, that's fine. Do it that way. Would there potentially, well, okay, that's fine. I don't want it.
Then you just plug in the 5/3?
Yep, exactly. Yeah, we plug in. So we're going to evaluate this from the difference between the antiderivative evaluated at pi thirds and at 0. So what's this answer going to give us over here? X, pi thirds minus 0 is just pi thirds, right? At 0, the value of the blue expression just becomes 0, right? So this one is pretty simple. This one just becomes 4/3 pi, okay? Minus, what are we going to get here? At pi thirds, what's the sign of pi thirds? Square root of 3 over 2, good. Right, so 3 times the square root of 3 over 2. Good, okay, plus pi thirds minus, what's the value at 0?
Oh.
0, isn't it?
0.
Right. So then we just end up with the overall area. 4/3 pi minus this whole thing. I'm going to be subtracting a 1/3 pi from that, aren't I? What's 4/3 pi minus 1/3 pi? Pi. Minus.
So that's the gray area?
Yep. Some might argue all of calculus is sort of a gray area.
Especially for me, it's
Okay.
not a gray area, it's a black area.
Okay. Does that make sense?
So is the 0 come from?
0 comes from, because when we evaluate, when we plug 0 in
Oh, okay.
to both parts of that, they both go to 0.
Okay.
Yeah. So what this is if we call this thing right here capital F for the antiderivative, this is f of pi thirds, and that's f of 0.
Okay.
Okay. All right. Any others on this one? Okay, hold that thought for just a second. And any of the second fundamental theorem ones, Kendall, do you have a question on one of those, or are you unsure about one of those?
Yeah, I can't remember which one.
How about if I just go back to you tell me when I get the one that looks good.
Okay. I think it was like the last one.
Okay. Oh, I forgot, this thing takes forever in Chrome, I don't know why.
Can I,
Something I should disrupt.
can I, ask you the riddle now?
Okay, what's your riddle?
Alright, this one's a good one. Alright, so, what do you take as much as you give back? Or leave behind, excuse me. What do you take as much as you leave behind? What do you take as much as you leave behind? Oh, I'm gonna do the one that I told you. This one's stupid, alright? What can you draw? What can you, 7th grade, it was like a 7th grade physics. It wasn't really physics, it was
It's a third of the speed of sound.
watered down.
Me too.
Oh, yeah, physical science. It had something to do with this something, this, PHYSI something,
Okay, so something like this. Now, I'm not gonna do this one, because I really want you to do this one, this is a good question. So construct a function of that form that satisfies these conditions. Now, you want the derivative to be cosine squared 3x, right? Okay, so the derivative of this function that you're sticking in there, right? Okay? And you want the value of the area to be -4 when x equals 5. Okay? So this is a really tricky question. You don't have to do essentially any calculus on this one if you just think about it properly. Let's just remind ourselves, what is the second fundamental theorem? What's the derivative with respect to x of an area function, right? Of f of t dt from some constant to, what did I call it, g of x? And g of x could be simple, it could just be like x too, right? G of x is x, it makes it really simple. But what's that equal to? F of g of x times g prime of x, yeah. So if g of x is just x, that would just become f of x, right? If g of x equals x. And what would g prime of x be if it were just x? 1. So it would just be that, wouldn't it? Right? Is that making sense?
Mm-hmm. That makes a lot more sense.
Okay, so that's going to make this pretty easy then, right? So you just want to pick the one. In fact, really, that first part, they didn't give you much of a choice, did they? I mean, all the integrands are the same. Does that part make, that's what it has to be though, doesn't it? If you want your answer to be cosine squared of 3x, then that's what the area function needs to be, right? Because look at the pattern. That, right? Okay. You have to just choose your limits so that the area is going to work out to be 5. But notice that we have this plus c at the end. I forgot to put that in there, didn't I? Well, I guess I didn't do the whole thing. Right, so really this is that constant at the end is important. How are you going to know? I don't want to tell you anymore. I don't really want to tell you anymore. Yeah, I won't tell you anymore. I mean, this. Think of this. Think of this one hint though. This part right here. When you do the second fundamental theorem, you get this function of x. Well, I mean doesn't have a set value. It depends on x, right? Okay, But you want your answer to just be constant, don't you? Right? So how are you gonna choose the value of x? Because it wants you to pick x. How are you gonna choose the value of x in such a way that this area plus the constant has a value of -4? Right? So you're picking the value of x, the upper limit. See what I'm saying? Okay, and you get to choose the value of c, so one of those values of c is gonna make sense. Anybody want to tell me what, just for this one, you're gonna get different when you do your own, but for this one, what's the answer gonna be?
B. C.
D.
A.
All of them.
B.
Hell
That's
yeah.
good.
D. Oh, that's right?
Yeah, how
Oh,
come?
I had the X here wrong.
How come?
Just looks right.
It just looks right. Okay, well, the derivative, does it fit the bill? Is the derivative cosine squared 3x of this guy? It is, isn't it? Right? Because if I take this one right here, dy dx would equal, I've got two parts. I've got this part that's an area function plus this constant at the end.
Yeah.
Derivative of a constant is always 0, so the derivative of that part's just gonna go away, right? The derivative of this part
Goes away 'cause of the dt at the end.
exactly, yeah, right? By the second fundamental theorem, this is just equal to cosine squared 3x, isn't it? Right? So, check. Got it. Okay, y equals -4 when x equals 5. Okay, is that true? Why is that true? If x is 5, what's that saying? Regardless of what this function in here is, doesn't even make any difference. If I'm taking an integral from 5 to 5, yeah, the width of that area is what? 0, so what's the area have to be? Yeah, right, okay, in other words, the width of this part right here, if that's a 5, that has to be 0, doesn't it? Because it's over no, right? Make sense? So all we're left with is 0 minus 4. Wow, that's pretty good. Okay? All right. Okay, maybe you're, I don't know, you wanna go to the lab for the rest of the time?
Yep.
Okay.